Alright, let's continue. Let me open the table of content first. Okay. We are on chapter 23, complete virtual memory system, and still on section 23.1 here, VAX or VMS virtual memory. Okay, let's take a look at that. Okay, we are in this chapter. We have to take a look at this, right? And then let's take a look at this, a real address space. One neat aspect of studying VMS, the operating system of the VAX machine, I guess, VAX 11 architecture, is that we can see how a real address space is constructed on figure 23.1. Thus far, we have assumed a simple address space of just user code, user data, and user heap. But as we can see above, a real address space is notably more complex. Above, oh, this one. Well, let me read this first. A real address space is notably more complex. For example, the code segment never begins at page 0. Oh, okay. This page instead is marked inaccessible in order to provide some support for detecting null pointer access. Alright. Thus, one concern when designing an address space is support for debugging. One concern when designing an address space is support for debugging, which the inaccessible 0 page provide here in some form. Oh, support for debugging. The inaccessible 0 page provide the debugging support. Interesting. Perhaps more importantly, the kernel virtual address space, that is its data structure and code, is a part of its user address space. Perhaps more importantly, the kernel virtual address space, that is its data structure and code, is a part of its user address space, On context switch, the operating system changes the P0 and P1 register to point to the appropriate base table of the soon-to-be-run process. However, it does not change the system space base, and bound register, and as a result, the same kernel structure are mapped into its user address space. Is a part of its user address space. Okay. To point to the appropriate base table of the soon-to-be-run process. However, it does not change the system space base. Again, previously we assume S as the system space. This one system space S, right? So it does not change the system space base and bound register, and as a result the same kernel structure are mapped into its user address space. The kernel is mapped into its address space for a number of reasons. This construction makes life easier for the kernel. When, for example, the operating system handed a pointer from a user program, for example on a write system call, it is easy to copy data from that pointer to its own structure. Okay. The operating system is naturally written and compiled without worry of where the data it is accessing comes from. If in contrast the kernel were located entirely in physical memory, it would be quite hard to do things like swap pages of the page table to disk. If the kernel were given its own address space, moving data between user application and the kernel would again be complicated and painful. With this construction, now used widely, the kernel appears almost as a library to application, albeit a protected one. One last point about this address space relates to protection. Clearly, the operating system does not want users' application reading or writing operating system data or code. Thus, the hardware must support different protection level for pages to enable this. The VAX did so by specifying in protection bit in the page table what privilege level the CPU must be at in order to access a particular page. Thus, system data and code are set to a higher level of protection than user data and code. An attempt access to such information from user code will generate a trap into the operating system and, you guessed it, the likely termination of the offending process. An attempt access to such information from user code will generate a trap, right? And then most likely result in the termination of this process. Let me check this figure 23.1, the VAX/VMS address space. Okay, page 0 invalid, alright. Then user code, user heap, user stack. Okay. Thread table, kernel data, kernel code, kernel heap, alright. Unused, interesting. There's unused space here. So there's, what is it called? A maximum of kernel heap allocation. Is that it? Interesting. Alright, I'm kind of curious about this. Maybe something like this. page 0 inaccessible provide support for debugging. Why making page 0 inaccessible? Okay. Inaccessible provide some form of support for debugging, I guess, in VRX VMS operating system. I mean, I'm not sure if Linux system also using the same mechanism or not. Okay. There's trap table, kernel data here. Yeah, the system space, the S here. Okay, let me read this. Wait. To provide some support for detecting null pointer access. Oh. Is making page 0 inaccessible related to the null pointer access debugging? I'm not sure. Okay. Alright. Aside, why null pointer access cause seg fault? The segmentation fault, You should now have a good understanding of exactly what happens on a null pointer dereference. A process generates a virtual address of 0 by doing something like this. Okay, set p equals 0 on some system null in here. What is it called? Represent as 0, I guess. The hardware tries to look up the virtual page number, also 0 here, okay, in the translation look asset buffer, and suffers a TLB miss. The translation look asset buffer miss. The page table is consulted, and the entry for virtual page number 0 is found to be marked invalid. Thus we have an invalid access, which transfer control to the operating system, which likely terminate the process. On Unix system, processes are sent a signal which allows them to react to such a fault if uncaught. However, the process is killed. Alright. Maybe providing the page 0 as inaccessible have anything to do with the null pointer access? Maybe. Okay, page replacement. The page table entry VTA in VAX contains the following bits: a valid bit, a protection field 4 bits, a modify or 30 bit, okay, a field reserved for operating system use 5 bit, and finally a physical frame number PFN to store the location of the bits in physical memory. The S2 reader make note no reference bit. Right. Let me take notes, I guess. PTA in operating system contains 5 bit, okay, and then protection bits, 4 bits, divide or 30 bit, okay, a field reserved for operating system use, bits reserved for operating system use 5 bits, and finally physical frame number PFN to store location of the bits in physical memory. Okay, physical frame number. Okay. The S2 reader make no reference bit. Thus, the VMS replacement algorithm must make do without hardware support for determining which bits are active. The developer were also concerned about memory hogs. Oh, okay. Programs that use a lot of memory and make it hard for other programs to run. Most of the policies we have looked at thus far are susceptible to such hogging. For example, LRU or least recently used is a global policy that doesn't share memory fairly among processes. To address these two problems, the developer came up with the segmented first in first out replacement policy. The idea is simple. Each process has a maximum number of bits it can keep in memory, known as its resident set size, RSS. Okay, each of these bits is kept on a first in first out list. When a process exceeds its RSS, the resident set size, the first in bits is fixed. Okay, first in first out clearly does not need any support from the hardware and is thus easy to implement. Of course, pure first in first out does not perform particularly well, as we saw earlier. To improve first in first out performance, VMS introduced two second change lists. where bits are placed before getting evicted from memory. Oh, okay. Specifically, a global clean page free list and dirty page list. When a process P exceeds its RSS, a page is removed from its per process first in first out. If clean not modified, it is placed on the end of the clean page list. If dirty modified, it is placed on the end of the dirty page list. Oh, so maybe we have some kind of trash bin, maybe something like that. We have trash bin for the clean page and trash bin for the dirty page. But then we need to free, or what is it called? We need to get out the page from this list, I assume. Well, let's continue first. If another process key needs a free page, it takes the first free page of the global clean list. However, if the original process P fault on that page before it is reclaimed, P reclaim it from the free or dirty list, thus avoiding a costly disk access. Okay, so if I understand correctly, wait a minute, the bigger this global second change lists are, the closer the segmented first in first out algorithm performs to list listener use. So if I understand correctly, let's say we have some bits from process P, right? Go to the clean page free list. If it's not modified, and then go to the dirty page free list if the page modified. Okay, resident set size, and then if the process P access the affected page again, page fault, right? Process P reclaims it. Process P reclaim the page back from free list, I guess. Thus avoiding a costly disk access. Okay. Maybe it is some kind of, maybe like the trash bin, something like that. And if the previous process needs it again, they can reclaim it as long as other process reclaim that page the page back from free list as long as other process have not reclaimed the page. Maybe something like that. Oh wait, if the process be access trying to access the affected page again, process B reclaim the page back from free list as long as other process have not claimed the page. As far as I understand, maybe something like that. The bigger this global second change list, the closer the segmented first in first out algorithm performed to list recently used. Another optimization used in VMS also helps overcome the small page size in VMS. Another optimization used in VMS also helps overcome the small page size in VMS, specifically with such small page, this input-output during swiping could be highly inefficient, as this do better with large transfer. Okay, to make swiping input-output more efficient, VMS add a number of optimization, but most important is clustering. Okay, with clustering, VMS group large pages of pages together from the global dirty list, okay, and writes them to disk in one file swap, thus making them clean. Okay, clustering is used in most modern systems as the freedom to place pages anywhere within swap space, as the operating system group pages, perform fewer and bigger writes, and thus improve performance. Is used in most modern systems. This one. Clustering is used in most modern systems as the freedom to place pages anywhere within swap space lets the operating system group pages. Okay. Perform fewer and bigger writes, and thus improve performance. Alternate tricks VMS had two other non-standard tricks: dimension zeroing and copy on write. We now describe this lazy optimization. One form of laziness in VMS and most modern systems is dimension zeroing of pages. To understand this better, let's consider the example of adding a page to your address space, say in your heap. In a naive implementation, the operating system responds to a request to add a page to your heap by finding a page in physical memory, zeroing it required for security, otherwise you'd be able to see what was on the page from when some other process used it, right? And then mapping it into your address space, that is setting up the page table to refer to that physical page as the sire. But the naive implementation can be costly, particularly if the page does not get used by the process, right? With dimension zeroing, the operating system instead does very little work when the page is added to your address space. It puts an entry in the page table that marks the page inaccessible. Okay, there's very little work when the page is added to your address space. It puts an entry in the page table that marks the page inaccessible. If the process then reads or writes the page, a threat into the operating system takes place. When handling the threat, the operating system notices, usually through some bits marked in the reserved for operating system portion of the page table entry, that this is actually a daemon 0 page. At this point, the operating system does the needed work of finding a physical page, zeroing it, and mapping it into the process address space. If the process never accesses the page, all such work is avoided, and thus the virtue of daemon zeroing. Okay, I assume this is some kind of placeholder, maybe. It puts an entry in the page table that marks the page inaccessible. Maybe this entry is the placeholder in the page table, and then when the process needs that, right, then the operating system do the work of finding the physical page, zeroing it, and then mapping it into the process address space. Yeah, maybe something like that. I think the page fault kind of thing. Maybe. Okay. So when the process never accesses the page, right? The operating system didn't need to find a physical page and then zeroing it and then mapping that. The operating system did not need to do all this work. Yeah, all such work is avoided. Okay. Another cool optimization found in VMS, and again in virtually every modern operating system, is copy on write, COW for short, I guess. The idea, which goes at least back to the 10x. I'm not sure how to pronounce this. Okay, 10x operating system is simple. When the operating system needs to copy a page from one address space to another, instead of copying it, it can map it into the target address space and mark it read-only input address space. Copy a page from one address space to another. Instead of copying it, it can map it into the target address space and mark it read-only input address space. If put address space only read the page, no further action is taken, and thus the operating system has realized a fast copy without actually moving any data. Oh, wait a minute. When the operating system needs to copy a page from one address space to another, Instead of copying it, it can map it onto the target address space and mark it read-only input address space. If put address space only read the page, no further action is taken, and thus the operating system has realized a fast copy without actually moving any data. If, however, one of the address space does indeed try to write to the page, it will trap into the operating system. The operating system will then notice that the page is a copy on write page and thus lazily allocate a new page, fill it with the data, and map this new page into the address space of the faulting process. The process then continues and now has its own private copy of the page. Okay. So the copy on write in here means, as far as I understand, we are only copying the page, right? We're only copying the page when the process need to write to those page. If the process only need to read, the operating system did not really copy that and just and just map it into the target address space, or maybe we can think of this like linking that page into the address space, the target address space, and mark it read only. And because it is read only, when the process, the target process, I guess, or one of the process wants to write to that read-only page, it will trigger a trap into the operating system, and the operating system will then copy the page. That is, allocate a new page, fill it with the data, and map this new page to the process that try to write to the page. Maybe something like that. The process then continues and now has its own private copy of the page. Okay. Alright, copy on write is useful for a number of reasons. Certainly any sort of set library can be mapped copy on write into the address space of many processes. Any sort of set library can be mapped copy on write into the address space of many processes, saving valuable memory space. In Unix system, copy on write is even more critical due to the semantic of fork and exec. As you might recall, fork creates an exact copy of the address space of the caller. With a large address space, making such a copy is slow, right, and data intensive. Even worse, most of the address space is immediately overwritten by a subsequent call to exec, which overlay the calling process address space with that of the soon-to-be exec program. By instead performing a copy on write fork, the operating system avoids much of the needless copying and thus retain the correct semantic while improving performance. Okay. Okay, let me read the aside where they read this one. Now let's read this one. I think I haven't read this aside. As it turns out, you don't need a hardware reference bit in order to get some notion of which bits are in use in a system. In fact, in the early 1980s, Babaglu, I most likely pronounced that wrong, and Joy showed that protection bits on the VAX can be used to emulate reference bit. Protection bit on the VAX can be used to emulate reference bit. The basic idea, if you want to gain some understanding of which bits are actively being used in a system, mark all of the bits in the base table as inaccessible, but keep around the information as to which bits are really accessible by the process, perhaps in the reserved operating system field or bits portion of the base table entry. When a process accesses a bits, it will generate a trap into the operating system. The operating system will then check if the bits really should be accessible, and if so, revert the bits to its normal protection, that is, read-only or read-write. At the time of a replacement, the operating system can check which bits remain marked inaccessible and thus get an idea of which bits have not been recently used. The key to this emulation of reference bit is reducing overhead while still obtaining a good idea of bits usage. The operating system must not be too aggressive in marking bits inaccessible, or overhead would be too high. The operating system also must not be too passive in such marking, or all bits will end up reference. The operating system will again have no good idea which bits to evict. Alright. Okay, that is one of the aside, emulating reference bit. Then let me read the tip here. Be lazy. Okay. Being lazy can be a virtue in both life as well as in operating system. Laziness can put off work until later, which is beneficial within an operating system for a number of reasons. First, putting off work might reduce the latency of the current operation, thus improving responsiveness. For example, operating systems often report that writes to a file succeeded immediately and only write them to this letter in the background. Second, and more importantly, laziness sometimes obviates the need to do the work at all. For example, delaying a write until the file is deleted remove the need to do the write at all. Laziness is also good in life. For example, by putting off your operating system project, you may find that the project specification bugs are worked out by your fellow classmates. However, the class project is unlikely to get cancelled, so being too lazy may be problematic, leading to a late project, bad grade, and a sad professor. Don't make professor sad, right? So basically the operating system procrastinate to do the work and improving responsiveness by procrastinate. Is that what happened here? Yeah, that is interesting. Okay, the Linux virtual memory system. Alright, you know what? Let's continue this on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.